you either missed the menu or you missed the bottom. What I'd like to do today is to continue on chapter 11. Just briefly, I want to show you some of the materials that I have posted. Besides the lectures, I've updated the chapter 11 notes, so you might want to download them. And also, I have the chapter 12 notes are incomplete. That is, I haven't converted all the code to Markdown from LaTeX. But the first section is, and what I'd like to do today is finish chapter 11 and talk about the first section in chapter 12. Chapter 12 really should probably be divided into two chapters. One chapter you might call experimental design, and the other chapter, the analysis of variance, because quite a bit of it deals with the analysis of variance, and other parts deal with controlling variability, which is what design is all about. So at any rate, you might want to download those two sets of notes, but I will be updating the chapter 12 notes. When did I say the chapter 9 assignment was due? I said at the end of next week.
Oh, that's what it was. You said Friday before the exam.
Yeah, the exam is on Monday. Right. And I'm going to be putting chapter 10 up within the next couple of days. You have a long weekend, and I may even put 10 and 11 up, even though we won't get them graded before the exam. This will give you an opportunity to work on them before the exam, and which I think will be an important study aid. So I'll be putting up both chapters 10 and 11. 12 is a fairly long chapter, and we'll have to see. There might be more than one assignment associated with it. We will probably get through this week. We'll probably get through the first three sections of chapter 12, which are the design sections. One could argue that you should maybe do the analysis of variance first and then do the design after that. That's not the order of the book. So let's go into RStudio. I'll set this as the working directory, and actually I'm going to clear this code. I'm going to clear the console. One of the things I discovered, and I believe the problem with the graphs not showing up, is that this window has to be big enough, or it simply doesn't. It can compress the graph to a certain point, but if the area of that lower right window, or wherever you have that window, is too small, it won't do it. So when we look at graphs, we're probably going to have to either open it up or at least make it bigger. So we're in chapter 11. Let's go ahead and knit this. Let me just very briefly review where we've come from. We're talking about two types of models, the random effects model and the fixed effects model. The fixed effects model is what we have done Looks like I'm inconsistent in my title headings. I'll have to go back and look at that. The fixed effects model is mu plus alpha sub I plus epsilon sub I j. And the epsilons are the only thing that are random, and they're II independently normally distributed with a mean of 0 and a variance of sigma squared. And by the way we construct the model, the sum of the alpha sub i's equals 0, but as I mentioned, there are different ways you can construct a model when you have equivalent tests. So we're interested in whether or not the means are all equal. And we can do that with an f-test. And the mean square for error estimates sigma squared. And then the mean square for among the treatments estimates sigma squared plus the sum. Yeah, that's the sum of the alpha sub I. I couldn't see it from here. The sum of the alpha sub I squared over a minus 1, if a is the number of treatments. The random effect model looks the same, except that we're making a different assumption about the alphas. In addition to the epsilons being random, we're assuming the alphas are random with a mean of 0 and a variance of sigma squared sub a. And this is also called a variance components model. We're interested in the sigma squared sub a in particular. We're interested in how large that is, perhaps among the total variability. And so we're testing that it's 0 versus it's greater than 0. It can't be negative, it's a variance. And we can estimate sigma squared by the mean square error, as we mentioned before. And the mean square for A estimates the sigma squared plus n times sigma squared sub A. And so if you wanted to solve for n, if you wanted to solve for sigma squared sub A or sigma hat squared sub A, you can get that by taking the difference in the mean squares and dividing by n. And I'll get that in a second. Let me just say that I've treated this as all the sample sizes are the same. That doesn't have to be true for either of these models. If it's not true, in other words, if j goes from 1 up to n sub I, so n depends upon the ith group, then you get a slightly different, when you're looking at, as we'll see in a moment, the expected mean squares for what I've called ms sub a, the among mean square. If you take the expected value of that, it's no longer just n. And in the top, what happens is in a fixed effects model, the n factors out because they're all equal, but what it really is the sum of the n sub I alpha sub I squared. But if the n sub i's are all equal, the n factors out. Now, the mean square for error for the MSA, the expected mean square here, is a little bit different. Calculating the adjustment is a little bit more difficult. That's the type of thing that you do in Stat 513, where you may compute these exactly. In this course, we don't go into the details of that. Well, we know that the follow-up procedure for the fixed effects model will be multiple comparisons of some sort, of pairwise comparisons, orthogonal contrast, etc. So that's in Chapter 10, and we've done that in some depth. If you're looking at variance components, what you want to do is estimate the variance components as well as what we call the intraclass correlation coefficient, or the ICC. And that simply, it's sort of like an r squared, or the square root of an r squared. I mean, well, it's more like an r squared. It's going to be between, the way we define it, it's going to be between 0 and 1. And it's like 1 minus the error variance over the total variance. And that can be written as the variance among variance of sigma squared sub a, in other words, this term right here, over the sigma squared total. Now, when you get the estimate, you know, I said that the mean square error will estimate sigma squared. I could put a subscript e on that to indicate. But how do I estimate sigma hat squared sub a? Well, the sigma squared total is equal to the total variance, the sum of the two variances, which is sigma squared plus sigma squared sub A. And if you estimate, that, you can see by sort of solving, if you take the mean square error for A minus the mean square error for E and divide by N, that's one way you could think of getting an estimate of A. And that you can see from here, that the mean square for A is equal to this. And if you solve for A, now notice that hat actually goes over both components. And so this isn't strictly true. In other words, it is not necessarily the case, in fact, that my estimate sigma squared sub A, the hat on it, is even positive. And the reason is the mean square, if I look at this equation right here, the mean square among can be smaller than the mean square within. You have an f-test, and that f-test goes from 0 to plus infinity. The mode is at 1, and you'd expect that you'd expect the value around 1 if the null is true. Because if the null is true, what you're saying is that the sigma squared A is 0, and therefore that ratio for the numerator and denominator should be about the same. And so you'd expect an f of about 1. But because of variability, in fact, f can be less than 1, which implies the mean square for the among can be less than the mean square of n. Now, if you look at JUMP and SAS and so forth, you'll see that there are different adjustment procedures that we can do to get these variance components, which guarantee that they're not going to be negative. One of the most common is a restricted maximum likelihood estimator. And so, for example, I'm going to hopefully show you this in JUMP in a little bit. The restricted maximum likelihood estimator sort of guarantees that you're between 0 and 1. You cannot be less than 0 when you're estimating your variance components. So, we're interested in the variance components and estimating them, and we're also interested in what percentage or what proportion of the total variability is explained by the one I'm interested in, which is sigma squared sub A. Now you notice the R squared we had previously in Chapter 9, where we had the R squared. It's 1 minus SSE over SST. Very similar form. However, the R squared measures a linear relationship between the X and the Y. In this case, the X is a factor. And so we're not talking about a linear relationship here. We're talking about any relationship. Is there any relationship between the factor and the outcome variable? And if that's the case, then we would expect R sub I to be positive and not real near 0. So again, the two hypotheses, just to summarize, the two hypotheses we're interested in the FIM model, we're interested, that's also called the Model 1. We're interested in the alpha is all 0, and in the RIM model, we're interested in the sigma squared sub A is 0. So even though the form of the model looks a lot alike, what we're testing is different. The expected mean squares is something that you should learn. Now, again, those expected mean squares get modified if the n sub i's are not equal. But that's a very common case. So it's not. I don't want you to go away with the impression that we have to have equal sample sizes. We don't. But there are some adjustments. For example, for the FIM expected mean squared for among, it's an n sub I, not an n, and it goes inside the summation. So this would be an n sub I, and it would go inside. Whereas over here, this n is not really an n. It's a function of n, and it reduces to n if the sample size is all equal, but it's more complicated. I may give you that in the notes. It's not in the book, but I may give you that in the notes. I'll probably stick them in at some point, and then I'll show you. Now, when we get to the assumptions, for the assumptions for the two models, in some ways they're the same in the sense that we fit the model and we look at for example, we look at the residuals and we look at normality of the residuals. Now, that's not quite correct for the random effects model, But generally speaking, we can do that. When we do the assumption of normality, there's quite a few things that we could do. And I'll go through this in a minute, but we can look at a residual histogram. But I recommend, if you're looking at normality, unless you have a larger sample size, that can be pretty unstable. And it's not maybe the best way to look at it. It's better to look at the normal probability plot. And so, or the box plots. In this case, the side-by-side box plots have the advantage of not only, if you have symmetry among those boxes, and the boxes and the extents of those boxes to the min and max are about the same, not only does that indicate normality, in other words, if the median's sort of in the middle of those boxes, and the size of those boxes in terms of their vertical extent are about the same, the vertical extent, if they're about the same, would indicate that the variances are equal, and that's another assumption. So by looking at that, I get a pretty good idea, do I have normality? I can certainly tell symmetry, because if you have symmetry, that bar in the middle of the box should be about in the middle of that box. Now, don't expect it to be exactly the case. But remember, the residuals I plotted were not, these are the individual points for each of the three groups. In the first plot I did up here, these were the residuals after fitting the model. In other words, those were the residuals from the model. You don't just plot the raw data, and this is a mistake a lot of people make. They'll plot the raw data for all observations across all groups. Don't expect that to be normal, because if you had all your groups the same and one group different, they would look like outliers. So you shouldn't just plot the y's. You should plot the y minus the y hats, the residuals, because those are what should be normally distributed. Because otherwise you're mixing in the group differences, and that's not what you want to do for the residual plot. So at any rate, the box plot's a very nice plot, and also the normality plot. These two plots right here, I think, are better than the residual plot. Now, if you're looking at the residual plot versus the y hat, that may give us some information, and we're going to get back to that point in a minute. But so those are some plots you can do, and you can indicate that maybe there's some slight deviation, in the upper tail. And if you look at the residuals, you can kind of see that maybe something's going on. Again, that's the normal plot of the residuals, not the raw data. And what about equality of variance? The book has two tests, Hartley's F-max test and the Bartlett's test. And I don't think Hartley's test is actually in the book. It just takes the maximum variance over the smallest variance. And it looks and computes that as statistic. It's an F-type. It's an F statistic, and there's a table in the back of the book. I don't think it's in. Well, I haven't. It may be someplace, but I'm not sure where it is. It's not in where you would expect in the normal procedures. But Bartlett's test is, and it's probably a slightly better test, although they're often about the same. But again, what we're testing here is that the variances are all equal. Now, you can also do a test, which I didn't show you. You can actually do a formal test of normality, like there's something called the Kolmogorov-Smirnov test, for example. So there are various tests you can do for normality. Now, the problem with the normal test for normality, Bartlett's test for equality of variance, is they don't have a lot of power, unless you have large sample sizes. And therefore, the graphical methods perhaps give you more guidance in doing these formal tests. You're going to get a false sense of security. You're going to say, oh, I failed to reject. Well, the reason you may fail to reject is you don't have much power. If you don't have power, you have a hard time rejecting, even if you should reject. That's what we mean by not having high power. You fail to, type 2 errors is when you fail to reject when you should. Well, power is 1 minus that. So if the type 2 error is large, meaning you fail to reject when you should, then 1 minus the type 2, and that's 1 minus beta, because we call beta probability of the type 2 error. Then, of course, that's going to be small. So we can just do that Bartlett dot test. We give the same model, month tilde brand, and it will do the Bartlett's test. And you can see that the p-value is 0.8. It doesn't even come close. But if you look at the variances, it appears like there are some differences in those variances. I compute them up here, and you can see they go from 2.66 up to 6.12. And so you can see that there appear to be differences. The max to the min is 2.3 approximately, and yet we don't reject. Now, again, this is a very small sample size, so it's quite possible the variances aren't that different, and it's just the case of having a small sample. I'm going to come back to this in a moment with our code, but I want to talk about independence now because this is an important plot. If we have independence between the epsilons and the alphas, that's one of the... You're assuming that the epsilons are independent of each other, and you're assuming the alpha sub i's are independent of each other, but you're also assuming that the epsilons are independent of the alphas. So you're assuming there's no relationship between the effects due to the treatment and the error, or epsilons, the individual errors. And one of the ways we can check that out is by plotting the means on the y-axis. Well, it doesn't matter which way it goes, but by convention we put the means on the y-axis and the variances on the, the means on the x-axis and the variances on the y-axis. And you can see that there's a dropping off effect here. If, in fact, the variances didn't depend upon the mean, then there would be a horizontal. Those 3 points would be more or less horizontal, with some variation, of course. So this is indicating to us that we have some issue. Now, it's maybe not as bad as you think because this scale doesn't go down to 0. But nonetheless, you see that drop off as the mean is increasing, the variance is actually decreasing. It's usually the opposite. So now we could also do as I mentioned to you, we could do a fitted versus residual plot where we put the fit on the x-axis and the residuals here. And again, we expect a spread around 0. We don't want to see a pattern where one group may have an outlier and the rest of the points are above and so forth. You don't want to see a pattern here. This is sort of a case in this group 1 right here. You can see that I have 3 values that are high and then I have 1 low value. I don't know, it's not an outlier because the box plots didn't show it as an outlier, but again, that first group has one observation that appears to be quite different from the other 3. Okay. So if I go back and look at some of this, I was going to it actually will show up. Whenever I executed it, the console, it kicks in there and then it messes this up. But if you expand it up, you can see the plot. So it wasn't so much a problem of the margins. It's simply a problem that I was setting the window small so that you could see most of the console. And again, the side-by-side box plot, which I will have to pop up. So you can see how to do these, and here's the QQ norm. And so forth. And I'll skip the F max, but here's the Bartlett's test. And when we're doing independence, again, if we compute the means, we've already computed the variances and do the plot. I didn't do the variance. I skipped that over. Where did I do? Oh, here, the variances are done up here. And if I name them, and here are the variances. Then if I go down and plot the means versus the variances. That's interesting. Where is it? Let me make this big and try it. Yeah, it looks like if you actually have it set below, it actually gives you an error, and you can't even. You have to sort of move it up, and then it moves it down. The other alternative is to set this breaker in the middle. So I think if you would just set it by default, if you would set it someplace about there, probably, let's see if it just works. Yeah, it works, but you're still going to have to blow it up to make any sense of it. There's just not room. And you can't, I suppose you could make the console real small. But then you don't see the other output, so. It's kind of one of the flaws of trying to do 4 different cells. So I'd like to briefly talk about transformations. Let's go back here. And there are a couple situations. First of all, we want to do a monotonic transformation. In other words, if y sub I, if I have 2 observations, y sub I, and it's less than y sub j, then if I transform it with some function g, like the log, I like g of y sub I to be less than g of y sub j. Now, if we have a concave upwards, if we have a situation with a concave upwards, then a lot of times in that case, the log, either log of base e or log of base 10, it really doesn't matter because they're only a scale difference. Then perhaps we'll do that, but you might have to add a constant. So for example, if you're taking logs and you have a positive, a lot of times this occurs when you have large counts, and this also occurs when you have skewness a lot of times, and you want to reduce the skewness. If it's counts and you could have a 0, then we can't take the log of 0, right? So in that case, you may take the log of y plus 1. It could be that you could have numbers a little less than 0, minus 1, minus 2, in which case you may want to take the log of y plus 5. But again, it depends upon the size, the general size of y. The most common situations would be when I plot if I plot the y bars versus the s sub i's, which is the graph that we just looked at up here. When I have the means here and the variances here. When we look at that, that's what I'm talking about. When we look at that particular graph, if it's concave upwards, again, it implies that the variances are increasing with the means, then a log transform may work. And the most common instance is a log of y or the log of y plus 1. The log of y plus 1 is fairly common because a lot of times we are dealing with counts. And of course you can get a 0 count, and you don't want to take the log of 0. Now, suppose that it's increasing, but not exponentially. So in other words, it's going up in a linear way instead of a more exponential way. Then we may just take the square root, or the square root again of y plus c. Again, you could, if y could be 0, or less than 0, we want to add some constant to it. And so, again, if it's pretty much linear, then the square root transformation may not work. If it's concave downwards, and this would often be the case if you look in the book, where it increases and then it levels off. And this often occurs with binomial counts. That is, you actually have n trials, and you're counting how many successes in the n trials. But there's an upper limit of n. And this particularly might occur when you have smaller experiments, where the counts are not as large as in the case of the first one. It also might be the case that if you have percentages instead of doing counts, since you know n, you might take the count over n, right? So if I say I get 5 successes out of 20, okay, then that's 0.25. That's a proportion, or I could express it as 25%. So in those cases, it's one of the methods that's used is to try, it doesn't mean these things are going to work, but try the arc sine of the square root of y. And so those are some possible transformations. Now, in this case, we have one that's dropping off. And again, the square root transformation doesn't work there. It works when you go up, not down. It's not likely to work when you go in the opposite direction. Now, sometimes you can't find a transformation, and just let me say a few words about this. Sometimes the transformation, well, first of all, transformations by themselves often make it hard to interpret the results. Let's think about transforming y. We're talking about transforming y. Now, you could also think about transforming x. But in this, right now, we're talking about just the case of transforming y. One of the problems is you're interpreting results on a different scale. Now, a lot of times, the log scale makes sense. If I have, what happens if you look at our model here a minute. Suppose instead of being additive, mu plus alpha sub I plus epsilon sub ij, it's multiplicative. Mu times alpha sub I times the epsilon sub I. Suppose you have a multiplicative model instead of, this is an additive model. If you take the log of a sum, or if you take the log of a product, what is it? The log of A plus B. I said it wrong. The log of A times B. I'll get it right in a minute. The log of A times B. Well, it's the sum of the logs. So if I have a product of my effects, then taking the log of y will take the log of that product, which will be the sum of the logs of those terms. But again, I'm also taking the log of the epsilons. And so, you have to be careful in terms of how you interpret this. But a lot of times, we may assume that we have a multiplicative model instead of an additive model, and taking the logs is very appropriate because it linearizes, or it makes it, in this case, additive. So the log is a fairly straightforward one. If you're a biologist, it's very common to see things on a log scale. It gets more difficult when I start taking the arc sine of the square root, and that's my outcome. You see, if you have binomial data, I wouldn't really recommend you transform it if you know it's binomial. I'd assume that you should do a logistic regression, and you should fit it as a binomial. And if it's a count, maybe you should fit it as a Poisson model instead of trying to transform it. So generally speaking, I recommend that you don't transform unless you feel you really have to, that you fit the correct model. And usually the reason you have a problem is because you don't have normality, because you have some other distribution, like a Poisson or a binomial. And we have models to fit all those. Our Stat 555 class on categorical data analysis looks at those types of models. In the very end of this book, it talks about the logistic regression. We probably won't get to that, but it's there for you to look at. So transformations, we could take a look at a simple one. Suppose we're looking at, where did I read this in? I think this is the light bulb example. I have this light bulb example where I am looking at the months, the different types. How long do different brands survive, or if I'm looking at the distribution of survival time, or in this case, you're looking at the reliability of the light bulbs and trying to determine how long they burn before they burn out. So if we measure that in months and we have different brands, we could do an analysis of variance to compare the brands. Now, so we were fitting months as a function of brand, meaning that we want to see whether there's a brand difference. So when we do this, if we get, in this case, what I was doing is I was saying buy. I'm looking at. Oh, okay, here it is. This is the example where I have brand and months, and I'm looking at this drop-off. And again, the square root's not going to work in this case. It would work for a positive slope, but not a negative slope. Let's take a look at another example where we're looking at flies, and we're looking at 10 traps, and we have the 6 increasing levels of pheromone. And so we have this data, and I can take a look at this back in R, if I can find it. So I'm going to read the data in, and then I'm going to attach it, and there's the data. I think the levels go L1, L2 up to L6 or something like that. I think there were 6 levels. And then the actual number of flies, I don't know if there's a flies caught or what that actually represents. If I now plot this, we can see what? We can see that as the level increases, that the variance is increasing. So this is the mean, and the y-axis is the variance. We can see that there's an increase of the variance with the mean. And in fact, it seems like it's more than linear. It's not just a linear increase, it's more of an exponential. So what transformation does this suggest? Suggests the log, right? So if we continue on, let's next do a box plot of this. Now this is the box plot after I have taken the log. You notice the code, it's one of the problems if I want to see both of these. If you notice the code, it's the log of flies plus 1 till the level. Notice that this is, we have a mean difference, that's okay. But notice that the variance seems to be stabilized. So we don't have this dependence on the variance of it. Now this is a different plot. I haven't actually plotted the mean versus the variance. I think if you did the plot of the mean versus variance, if we did that plot, I think that you would see that it would pretty well level out. Because the variance in L5 and L6 don't seem much different than L1 and L2 and so forth. So the variances seem to be stabilized by taking the log. And normality doesn't seem too bad. If I look at that plot, I don't see too much of a problem. The normality seems reasonable. The equality variances seem reasonable. And so by taking the log, I think we had a significant gain in this case. Okay, are there any questions on that? Let me just quickly show you that I'm going to go in and connect to the server. I'm going to show you occasionally how to do things using JMP. Now JMP is some software that I'm not requiring for this course. It is on these machines, and it's something you can buy for, I think, $40. I can get directions on how you buy it. I think you either buy it through the WV bookstore with Mike Cooper's group, or you buy it through WVNet. I'm not sure. I'll check on that for you. So if you're interested in buying JMP for your home computer, You don't actually buy it. You license it, and it's a yearly fee. And one of the things that I've been hesitant about in terms of using this software too much is it's not just that you license. That $40 is a student account. Once you graduate, it's like $1,000. So,
Is there going to be a 513 course that doesn't use Jump next semester?
The reason that I'm teaching this course with an online course is because in the MPS program, Master Professional Studies, students can take this program completely online. But 513 is not one of the courses that's required for that. So, yes, I personally would like to see that, but I don't think it's going to happen. My problem, again, with using Jump is that it's, in some sense, it's quick, but it's limiting. There are a lot of engineers, and I mean, it is used a lot of places. SAS is a little more flexible, but SAS lets you program the data step, but it doesn't let you program procedures. And so you can do data management. You can also do data management in SAS, in Jump, but it's what you can do point and click, pretty much. Jump does have a scripting language, but again, it's the data step, or what is equivalent in Jump to the data step in SAS. So let me find, this is the equivalent thing. So we're looking at chapter 11, and I think initially we were looking at brand and pheromone. Those are the two. So if I go into Jump, it's a little deep, sorry. Now usually when I'm opening, I'm going to say make its best guess, and usually it does a good job. So these are the brands and the months, and these are very simple. First of all, you could just fit it Y by X, because it's okay that in this case, I have months by X, and I can say okay, and then I can do multiple comparisons and so forth. And we did this last time. But if you want to do variance components, so for example, if in fact the brand were a random selection of brands out of a bunch of brands, and that would be that would be an example. I'm not saying that's the case here, but if you had a random selection of brands out of this large group of brands, then the brand would be a random effect, not a fixed effect. And so if we sort of pretend like that's the case, then how would you do that in Jump? Well, in Jump, what you would do is you would say fit model, and again we want months as Y, and then we put brand down here. But we do want to do one other thing. We're going to tell it that it's a random effect. Okay, now again, remember I said that RML, the restricted maximum likelihood, by default that's what it's going to give you. So if I look here, I could use the book is doing the EMS traditional. The problem with the EMS traditional is you can get those negative estimates of the variance components, and so that can be a problem. I'm not saying it's a problem here, but it could be a problem. Now what typically is done in this EMS traditional, if it's negative, if sigma hat squared sub A is negative, you simply set it to 0. So I'll go ahead and leave it as recommended. I don't think it's a problem here. And if you just run it, then this actually gives you the variance component estimates. And we could actually run these side by side just to sort of see the difference. If I analyze fit model and I don't specify brand to be, if I specify brand to be fixed, so I don't specify it to be random, then you're going to see that in this case, we have analysis of variance table, we get our f-test, we estimate the effect test on brand, which in this case, notice that the p-value, whether it's an f-test, notice that right here for the model is the same as the brand. The model is the brand in this case because we only had one effect. If you had a two-way analysis of variance, that would not be the case. The model would be all the factors, and not in this case we just have one factor, so all the factors in fact is the one factor called brand. But you can see there's a bit of difference in terms of the variance component. These are the REMO estimates. For the variance component for brand is about 4.5. The residual is about 4.3. The total is about 3.85. So you can see that the ICC, does it give you the ICC? I'm not sure it does. Well, it does because the percent, it's giving the percent of total. And notice that the ICC will be about 0.5, a little bit greater than 0.5, because they're giving the percent of the total, and the total is 8.87. So I'm looking at the ratio of this, the 4.51 to 8.87. So it's about a little over 0.5 is the ICC. So you can get it here. So the brand variation explains about 50% of the variation. So there's a lot of variation in addition to the brand variation. So if, in fact, I had a random sample of brands out of a large group of brands, then the brand effect is about 50% of the total variation. Does that make sense? So that's how you do it in JUMP, and we just specify that it's random. Okay, any questions? Now, in JUMP, how would you do if I read in, well, again, I could, in this case, it's sort of coming up okay. I have the level and I have the flies, and these are counts. So if I analyze this data, I could fit it, and I'll just do it as a fixed effect this time. So if I do flies here versus adding it here, I can run it. And notice I get my least squares means, and I can also get my students' t's, which is Fisher's LSD, and you can see where the significance are. Actually, I think the red is significant, which means there are a lot of significance here. Well, we can look at it down here. Things covered by a common letter are not significantly different. So A is distinct from everything else. And you can see there's some overlap. So this is a straightforward thing. The only problem is, look at this graph right here. If you look at that graph, what do you see? You're looking at the residual versus the predicted, and notice that this is the residuals on the y-axis. Notice how it's getting bigger and bigger as the predicted gets higher, so as the means get greater. The means are the predicted values in the case of analysis of variance. So notice that the means are getting bigger, the variance is getting much greater. Okay. And that was that plot we saw when we did the, what's called the, we were looking at the means versus the variances in that plot. We saw that we had exactly the same thing, and therefore we said, well, okay, let's try to log. So how do you do it? Well, we have to define a new variable. We can define a new variable, which, we can do as, as a transformation by doing a new column. And so I'm going to have numeric continuous, and what I'm going to do is define a new formula. And if I look, I think it's under transcendental. I don't think it matters whether it's the log. It's log base e. I guess I could do it. And I'm going to do the log of that, and I'll take the log of flies, and then I'll put +1. So I have the log. That's going to be a new column. So notice that's the column here. I could have scaled back the decimal positions there, which I perhaps should have done. And I could have named it a little bit better. I could actually name it here, the log of flies or something like that. So at this point, then what you would do is you would go in and you would say fit model. And in this case, I would fit the log of flies versus level. And I'd run this. And we can see that from this plot that things are much better behaved. And we could actually look at the contrast on this transform scale using the same. I don't think there's a whole lot of difference. The A effect is no longer. The A effect is a bit different in that before there was a single A, so level 6 was kind of unique to itself, whereas now level 5 and 6 are not significantly different, and so forth. So this is how you do it in JUMP. Any questions? Okay, now what I want to do is start on, I'm going to quit this. Going back to R, I want to go into chapter 12. Now again, I gave you the notes, but if you get down beyond section 1, things are not sort of redone. I'm going to change the working directory, and now I'm going to knit this, I hope. So you notice that at some point I haven't redone all this stuff, but I have redone the first section. So I want to introduce this model today. There are several situations in which we have two sources of variability, but we have what's called nesting. So in other words, we're going to look at a model y sub ijk is equal to mu plus alpha sub I plus beta sub ij plus epsilon sub ijk. Now how is that different? Well, y sub ijk is the response of the ith treatment for the jth experimental unit within the ith date treatment and the k subsample. In other words, we can think of the k subscript as subsampling. Now there are certain situations, and the book gives a number of examples where this could be true. For example, you have 4 dyes, and you have 2. Oh, by the way, the alpha could be either fixed or random. So we're assuming that the alpha could be fixed or random, but both the beta and the epsilon are going to be random. So we're going to assume that we have 2 random effects here, the beta and the epsilons. Now before, for the random effects model, we had the alphas were random, and we had the epsilons were also random. This is an extension of that, but again, in this case, we can assume that the alpha effect can either be fixed or random, but the betas are going to be random, as are the epsilons. And so this is our model, and if you have, in this case, if we're doing dyes and we have 4 dyes, those 4 dyes are fixed. And then we have a random sample of bolts. A bolts is it's a roll of cloth. And then we sample, let's say, so we sample 2 bolts, for each of the 4 dyes. So that's 8 bolts altogether. So we have 2 bolts for each of 4 dyes, so that's 8 bolts. And then for each of the bolts, we sample 6 swatches, little pieces of material that we actually test. So that's 6 times 8 or 48 swatches. So there are 48 observations altogether. But the bolts are not crossed with the die, they're subsampled. In other words, a certain die goes on 2, and then another die goes on 2 different ones. It's not as if it's the same bolt that we're applying each die to. If that were the case, this would be what's called a factorial experiment. If we put each die on each bolt, but we're not, the bolts are specific to the die. In other words, you can think of the bolts as being nested within the die, and the swatches nested within the bolts. Because again, I get 6 swatches from each bolt. So we have a completely nested design. In this particular case, we have the bolts nested within dies and swatches nested within bolts. Now, sometimes when you're designing an experiment, you've got to be careful here, because I remember working with a guy in microbiology one time, and the way the experiment was designed was extremely convoluted. And if it gets too convoluted, your ability to make inferences significantly go down. So you may also have 10 roosters, each mated to 5 different hens, and then you randomly select 6 chicks from each hen. Now in this case, everything's random. In the first case, the dies are fixed, right? But the bolts and the swatches are random. In the next experiment, if I have roosters, again, they're going to be random. So the alpha is random, as well as the hens, which correspond to the betas, as well as the chicks, which correspond to the epsilons. So in the second case, everything is random. So here's our model. And again, the alphas, we can either have the sum of the alpha sub i's equals 0, or we can have the alpha sub i's are independently normal, mean 0 variance sigma squared, depending upon whether that main effect, the alpha part, is either fixed or random. It could be either. But we're assuming that the next 2 levels, that is, the beta and the epsilon, they are independent normal. But they have different variances. In other words, the beta is going to have a variance of sigma squared sub b, and a mean of 0, whereas the epsilon is going to have a variance of sigma squared, or if you want to call it sigma squared sub e for error, but generally when it's error, we leave off the subscript. So that's the model. So we're either going to test that the alpha sub i's are 0, or that, if for the fixed effects, or that the variance of sigma squared sub a is 0 for the rim model. And of course, the real error term is independently normal, mean 0 variance sigma squared. Now, in terms of how we compute these things, first of all, you might ask, well, what are the degrees of freedom? What are the degrees of freedom? Well, we talk about what's called the total corrected sum of squares. And the total corrected sum of squares simply takes all observations minus the grand mean. Y bar by itself is the mean. In the first example, it would be the mean of all 48 swatches. It's the mean of everything. And if I take the deviations of the yijk's from y bar, square it, and add it up over all possible ij's and k's. But I've corrected for the mean by subtracting out the mean. Computationally, if you were doing this on a calculator, you would compute these for quantities. You would compute t, which is the sum of squares of everything, and then the correction factor, which is the sum of everything squared over a, b, n. A is the number of levels of A, the A term effect, and B is the number of levels of the B effect, and N is the number of at the lowest level. Now again, I'm assuming the sample size is all the same. That doesn't have to be the case. And then I get, these are the computing formulas for the A and B. And by the way, I've sort of sloughed over this because I'm using R, but the book actually, you might want to look at the book and how they calculate it in terms of, how do we calculate this? Now, the degrees of freedom, again, the treatment effect will be A minus 1, just like we had before. But then the experimental error within the treatment, and I'm using parentheses here to say experimental error within treatment, and then I'm going to refer to the next level down as a subsample or the sample within experimental units. So this will be A times B minus 1, and then I have a times b times n minus 1. Now, this is you can sort of see a pattern relative to the one-way analysis of variance, where I had a minus 1 and then I had a times n minus 1, but of degrees of freedom. So these are the sum of squares right here under definition. But again, if you in fact were doing it by hand, that wouldn't be the way you do it. You'd use the computing formula. But let me just indicate for the treatment effect, I'm looking at the y bar sub i's. Those are the treatment means, and I'm averaging over two subscripts, the j and the k. And then y bar is, again, the grand mean, where I'm averaging over all three subscripts. So in the case of the cloth example, there are 4 dies, and then for each die there are actually how many swaps are there? Well, there are 2 times 6. There are 6 bolts, each of which has 6. So there are 12 observations per die. 4 times 12 is 48. That's how you get it. So when I'm getting the die means, I'm getting the mean of 12 things for that die. Again, I'd refer you to the book to actually see the calculations. And then this mean right here, the y bar sub ij, it's a combination of the die and the bolt. And I'm just averaging over the swaths within a given bolt for a die. So I'm looking at y bar sub ij, and here I'm looking at the deviation from y bar I. How much do the y bars ij's vary about the y bar I? It's looking at that source of variation. And you can see how we can compute these. We compute A as A minus CF, whereas B is B minus A. And so that's how it's computed. Now the expected mean squares, which is sort of key to how we do things, and I don't think I'll have time for an example today, but just let me mention that the expected mean squares, we now have a sigma squared sub A, and a sigma squared sub B. And you can see for the random effects model, I get among samples within experimental units is sigma squared. That would be the expected mean squares for the error term. And then if I'm looking at the next level up, if I'm looking at among experimental units within the treatment, that will be sigma squared plus n times sigma squared sub A. And then if I look at the top level among treatments, that's sigma squared plus n times sigma squared sub B plus b times n sigma squared sub A. Again, this is assuming equal size samples, which may not be the case, but it gets a lot harder to compute those if it's not the case. So you can certainly do it. Now, if I were looking at a test, and my null hypothesis, suppose I'm testing the hypothesis, let's look at the random effects model. Suppose I'm testing in fact, for testing sigma squared sub B, it doesn't matter. How would I test the variation among the sigma squared sub B, that is the variation among the experimental units of treatment? How do I test that being 0? I look at the mean square for what over what as an f-test. I would be the among experimental units. I would be looking at this second line here. Notice that if this is 0, if this sigma squared sub B is 0 here or here, then these two are the same. All right, that ratio would be approximately the same, even if we put estimates in, and that would be the appropriate test to use the among experimental units in treatment as the numerator and the within or the among samples within experimental units as a denominator. If I take the ratio of that, it will give me an f-test. The degrees of freedom are going to be a minus 1 in the numerator and a times b minus 1 in the denominator. But I'm really interested in the sigma squared sub A, most interested in it. Or if I have fixed effects, I'm interested in the alpha sub i's all being 0. And again, what am I going to test by? And this is where people make a lot of mistakes. I don't test by the bottom one, the among samples within experimental units. Notice that I test by the middle one, the among experimental units within treatments. So again, I can carry out the F-test, and that's what I've indicated here. And I don't think we have time, but there's an example here that, let's see, did it? Okay, this is where I'll start next time with this example. But read section 1 and read section 2. We're going to cover 1 and 2. 2 is on block designs. This particular nested design is not really what I would call. It's not really what I would call experimental design in the sense of controlling variability. But the next section 2 is about block designs. That's specifically done to control variation. This nested is going to be contrasted with something we call crossed. Here we have nested factors, but one of the most common reasons you do analysis of variance is to do cross factors. And so that will probably be done after the exam, or maybe we'll get briefly started on it, but it won't be on the exam. Okay. Any questions? Okay. Stop recording then.